Good day, everyone. So we are reviewing Wetzel's Limnology textbook. This is edition number 4. We are on chapter 15, Phosphorus, and more specifically, we are looking at modeling relationships between nutrient loading and phytoplankton productivity. And we left it at this subsection B, modeling biological responses to nutrient loading. So let's get started. Based on these nutrient loading relationships, the loadings to a lake should be related to biological responses such as phytoplankton biomass and productivity, which is a rate measured as, for example, gram of carbon per meter squared per year. Early empirical predictions of chlorophyll A levels from phosphorus concentrations in lakes at spring turnover or during the growing season were later extended further with larger worldwide datasets. Within certain boundaries, the regression between phosphorus inflow concentration (Pi) as a proxy for loading and average annual chlorophyll A concentration (CHLA) is approximated by the concentration of CHLA chlorophyll A is equal to 0.55 by Pi over 1 plus the square root of tau W, and that member of the equation is raised to the power of 0.76, where tau W is the water residence time. Examples of these relationships are given in figure 15-15. Similar relationships have been found for many other lakes with only minor deviations. The annual rate of phytoplankton primary productivity, C, has also been related to the predicted phosphorus concentration. The nonlinearity of the log plot results from the light-reducing self-shading effects of dense phytoplankton populations at high levels of productivity and nitrogen limitation, which can replace phosphorus limitation in highly eutrophic lakes. Multi-compartment dynamic models that predict biological responses as a function of nutrient loading have also been developed. So I think here potentially like the C member that we are seeing here may be this value here rather than carbon. So gram of the primary productivity C here. It's a little unclear, however. Application of predictive models and data. The evaluation of the trophic status of a lake has great practical importance. The extent of eutrophication must be known before remedial corrective measures can be implemented in relation to the desired uses for any lake. Based upon a large data set obtained during an international program on eutrophication of the Organization for Economic Cooperation and Development, nutrient load eutrophication response relationship for lakes and reservoirs were quantified and evaluated. The analysis provided a potential basis by which predictions can be made of the changes in water quality that will occur from changes in the phosphorus loadings to phosphorus-limited water bodies. Analysis of over 200 water bodies permitted a general classification of lakes based on water transparency and concentration of phosphorus, nitrogen, and phytoplankton pigments, although any attempt at rigid classification of water bodies is subjective and fraught with exceptions. The general classification is useful. So before moving on, let's look at these figures and tables. Figure 15-15, regression relationship between predicted total phosphorus concentration and annual mean chlorophyll A concentration for selected alpine lakes. So all of this is logarithmic scale based on log 10. So this is the yearly average of chlorophyll A in milligrams per meter cube, and this is the predicted phosphorus concentration. And we already saw that term, and we saw it right here, I believe. Right here, P lambda. And they define P lambda as the average total lake concentration dissolved and particulate phosphorus component, both for dissolved and particulate phosphorus. So this the average total lake concentration. So and this is the formula how we obtain it. So What we glean from this is that as the concentration of phosphorus, the predicted concentration of phosphorus, total phosphorus in the lake increases, we have an increase in chlorophyll A, which makes sense. If phosphorus is the limiting factor, as you increase phosphorus concentration, you have more plants that are colonizing the lakes, including probably algae and cyanobacteria. And we can see that the relationship is about the same for these lakes. Like these three lake types. So we have Rust line and we have two alpine lake. Okay, figure 15-16, annual primary productivity. So in gram C per meter square per year as a function of predicted total phosphorus concentration. And here on the y-axis we have the primary production, so that's the C value. And on the x-axis, we have the predicted phosphorus concentration, P lambda. So here as well, the production increases as the phosphorus increases. No big surprise. Although we can see a plateauing out of that concentration, of that productivity, as the concentration increases. So past a point, even like the lake cannot produce more than it already does, even if phosphorus is not a limiting factor. Table 15-17, we have general trophic classification of lakes and reservoirs in relation to phosphorus and nitrogen. So we have the parameter on the left, and then we have the trophic status on the right here. And so we go from oligotrophic, nutrient poor, to hypereutrophic, which is nutrient rich. Total phosphorus, total nitrogen, chlorophyll A of phytoplankton, chlorophyll A maxima, worst case, and then the Secchi transparency depth. So as concentrations of phosphorus increases, we have the trophic status of the lake increases as well. It becomes more nutrient rich. The same for chlorophyll A and for nitrogen. So we also have like a large jump between the mesotrophic and eutrophic status, more than between oligotrophic and mesotrophic. And then the Secchi depth decreases drastically as the trophic status increases, as the nutrient availability in the lakes increase. The models permit predictions of the probability of oligotrophic, intermediate, or eutrophic conditions developing in phosphorus-limited lakes in response to various loading regimes. The literature on this subject is very large, for the models have been continuously tested, refined, and improved. As with all modeling efforts of natural and disturbed ecosystem, one must not permit the mathematical manipulations to become an end in themselves. Models based on many data points permit estimates of permissible loading rates of phosphorus and nitrogen while still allowing tolerable conditions of productivity. Considering a combination of influencing conditions, Volvider estimated very approximate provisional loading rates of nitrogen and phosphorus required to maintain lakes in a steady state. Rapid eutrophication is likely to result as loading is increased, although the predictive models have improved considerably since this 1968 analysis appeared. The tolerable loading level of 10 milligrams of phosphorus per meter cubes remained unaltered, while the excessive loading level had been increased slightly to 25 milligrams of phosphorus per meter cube. A simple production-based trophic state index, or TSI, uses phytoplankton biomass as a basis for a continuum of trophic states of lakes and reservoirs under both nutrient-limiting and non-nutrient-limited conditions. TSI is a unitless empirical parameter with values mostly between 0 and 100. TSI values increase as a lake becomes more productive. Log linear regression for TSI as a function of Secchi depth, chlorophyll A, and total phosphorus have been developed using pooled data sets. So TSI SD, where SD is the Secchi depth transparency, here we go. And CHL is chlorophyll A, pigment concentration in milligrams per meter cube, and TP is total phosphorus concentration. So we have like three equations here. So this is equation number 1, 15-11, then we have equation number 2, in equation number 3. Since the parameters exhibit seasonal trends, ice-free means are probably best for calculating TSI. TSI values of less than 30 are common among lakes and reservoirs of classical oligotrophy, and from 50 to 70 correspond to classical eutrophy. Hypereutrophic conditions are common at TSI values greater than 70. Figure 15-17, probable boundaries of the degrees of trophy of water bodies with differing annual mean values of total phosphorus concentrations left and chlorophyll A concentrations right. So on the y-axis we have the probability value between 0 and 1, and on the x-axis here we have first a set of numbers, the log 10 of the predicted phosphorus concentration, and the arithmetic log, and then we have the concentration of the predicted concentration of phosphorus in milligrams per meter cube in the lower values. So for oligotrophic lake, we have very high probability of having oligotrophic lake at a very low concentration of phosphorus, and then at the concentration, let's say, of about 50 milligrams of phosphorus per meter cube, our probability of having an oligotrophic lake is about 0. Mesotrophic, that is probably the narrower range that we have, narrowest range that we have. So mesotrophic starts like at 1 once again. So if we don't have much of a phosphorus, we could have still a mesotrophic lake. So there's somewhat of an overlap, very close to an overlap between oligotrophic and mesotrophic lake. So we still have like pretty high probability of having a mesotrophic lake as at concentration of phosphorus at about maybe 30-40 milligrams per meter cube, and then it crashes, and then we can have close to like a concentration of maybe 500 milligrams per meter cube mesotrophic lake, and then that is for eutrophic lake on the right side. So here we have the same. We have y-axis, the probability. On the x-axis, we have the arithmetic log of chlorophyll A, or the value in concentrations. And then we have like a couple curves here. And I'm not entirely sure why they are overlapping curves, but we have the same type of classification and the same type of analysis. Oligotrophic, mesotrophic, and eutrophic. And then table 15-18, provisional permissible loading levels for total nitrogen and total phosphorus, biochemically active in grams per meter square per year. So permissible loading, so we have mean depth on the left, permissible loading, and dangerous loading. So what is acceptable in terms of the amount of nitrogen to load on a lake, to input? So that would be 1 grams per meter square per year for nitrogen at a depth of 5. And as you can see, as you increase in depth, the permissible loading increases for nitrogen, not as drastically as it does for phosphorus. And then here, these are dangerous loading. So with this type of input, beyond that, you run the risk of having a nutrient-rich event. Deviation in the TSI relationships can be clarified by graphical expressions. Values below the 0 x-axis indicate the likelihood of something other than phosphorus limitation. Points above the x-axis suggest increased possibility of phosphorus limitation. Points to the right of the y-axis indicate transparency is greater than predicted from the chlorophyll A index. Points along the lower left diagonal to the left of the y-axis indicate reduced transparency from non-algal factors, such as high concentrations of dissolved organic matter or small particles of non-algal turbidity. So here what they are talking about this figure 15-18, and we have TSI value, and the TSI value CHL minus TSI value TP here, and then this is this is the Secchi depth. So here we have So let's once again refresh our memory what TSI stands for. TSI is a trophic state index. So the trophic state index for chlorophyll, so CHL, is chlorophyll A, minus the trophic index for total phosphorus. And then we have here on the x-axis trophic state index for chlorophyll minus the trophic state index for SD, which is the Secchi disk transparency. So that means when it's negative here, so where the value for chlorophyll A is less than the value for total phosphorus in terms of trophic state index, then we have, and then the value for chlorophyll is less than the value for Secchi depth, then we have high DOM, dissolved organic matter, or clay turbidity. Then we have a phosphorus limitation in here when the TSI chlorophyll is greater than the TSI of total phosphorus, so it's phosphorus limited. And then here we have so we have like when we have higher chlorophyll A than the Secchi depth, and we have higher phosphorus than we do chlorophyll A, then we have zooplankton that are grazing, and then it's non-phosphorus limitation because of course we have high phosphorus. And then here this quadrant of the curve is unknown. And then we can see that small particles versus large particles are here. The general trophic classification system for lakes has been extended to streams rather than use the chlorophyll A of cestone. The chlorophyll A content of benthic algae has been correlated to total nitrogen and phosphorus content in temperate streams. The correlations between total phosphorus and chlorophyll A for streams are distinctly weaker than in the case for lakes, but a set of approximate trophic categories has been proposed. Table 15-19 suggested boundaries for trophic classification of streams based on distribution of benthic chlorophyll content and nutrient concentration. So here we have the variable, the mean benthic chlorophyll A, maximum benthic chlorophyll A, systonic chlorophyll A, total phosphorus, total nitrogen. Oligotrophic, mesotrophic boundary, so we are right between those two categories, between oligotrophic and mesotrophic, and then here between mesotrophic and eutrophic boundary. So that's pretty much giving us like what kind of like boundary do we have between these trophic states, so between like first the oligotrophic, mesotrophic, and then the mesotrophic to eutrophic. So we would shift from oligotrophic to mesotrophic if we had concentration of the mean benthic chlorophyll A greater than 20 but less than 70, and greater than 60 and less than 200 for the maximum benthic chlorophyll A. Systonic chlorophyll A between 10 and 30. Total phosphorus between 25 and 75, so be a mesotrophic environment, and less than 25 will be very likely in an oligotrophic environment. And then total nitrogen in micrograms per liter between 700 and 1500. So this is kind of useful if you have like data for a lake and you're not sure if the lake is eutrophic, mesotrophic, or oligotrophic. You can then find out based on the concentration that you have detected. I think that's going to be it for today, and we'll finish up, I think, the chapter tomorrow. This is one of the longest chapters we went through, and appreciate your patience, and hopefully we'll pull through. Thanks again, and we'll see you tomorrow. Bye.